Get started. So first of all, a big thanks to all of you for being able to make it to my talk, especially during these unfortunate times. And I hope all of you are taking care of yourselves. So let me first start off by summarizing a little bit about Rachel's talk. So Rachel told us how you can construct this notion of a weakly secure or a partially secure functional encryption. And then she also told us that if you have, how you can construct indistinguishability obfuscation if you have a sub-exponentially secure functional encryption, which is a strong notion of security. So she told us about this, and this mainly follows a beautiful line of known results. The only step that remained was of being able to construct a sub-exponentially secure functional encryption, starting out from this weakly secure functional encryption. And so this is what I'm going to talk today. So the agenda of my talk is to present a security amplification theorem for functional encryption from LWE. And this is going to be a slightly technical talk, as I'll try to convey most ideas that were in the proof. At the same time, I'll try to hide some of the technical nitty-gritties in just to keep it light. If you want to read more about the proof, you can look at our full version, which appears in ePrint link 2018/615, and this is joint work with Prabhanjan and Amit. And the proceeding versions appears in Crypto 19, which is a merge with a paper of Rachel Lin and Christian Matt. So let me start off by kind of summarizing the goal of what we want to do. So we want to come up with a transformation that upgrades security of a functional encryption A in order to construct a functional encryption B. So what we want is that we want to start off with a functional encryption scheme which satisfies this notion, which I will denote by S epsilon security. I'll just define this S epsilon security in just a minute. But think of it as really the weak notion of security that Rachel was talking about. And we want to construct a functional encryption from this, which satisfies standard notion of security, and in fact, even sub-exponential notion of security, assuming some parameters are set appropriately. So for S epsilon security, the first thing that I want to tell you is like what these parameters indicate. So S will roughly stand for the size of the adversary in the corresponding security game. And by size, I mean the size of the adversary really as a circuit. And epsilon is the maximum advantage that any adversary of size S can have in the security game. So that was about security. However, in our transformation, we also want that whatever nice properties that functional encryption A had should also be satisfied by functional encryption scheme B. For example, if you had public key encryption, functional encryption to start off with, what you should land up should also be a public key functional encryption. And then suppose the functional encryption A had allowed for single function queries or Q number of queries, then functional encryption B should also support the same number of function queries. And then if functional encryption A had some efficiency properties such as sublinearity or compactness, about which both Rachel and Shweta talked, then functional encryption B should also have those nice properties about compactness and sublinearity. So at this point, let me remark something about sublinearity and compactness. This is really an important property, and the reason for that is that in all these transformations which allow you to construct I/O from functional encryption under sub-exponential loss, in all these transformations, a key requirement is that of some notion of sublinearity. And compactness is like a stronger requirement than sublinearity, but sublinearity, for those of you who might not remember, is just a requirement where you say that the size of the ciphertext is actually grows only sublinearly in the size of the function keys size of the functions for which the keys are issued. So it's proportional to something like 1 minus alpha times size of the function to the power 1 minus alpha, where alpha is some constant. 0, 1. So that's what sublinearity says. But it so turns out that this allows you to basically bootstrap any sub-exponential secure FE to IO. I won't be talking too much about sublinearity and compactness. Only at certain points, I'll just remark how our transformation preserves that. So now let me come to the definition that we're considering. So we're calling it S epsilon security. And we're going to define it using a simulation style definition. So for those of you who are following the FE literature, there are two kinds of definitions. The first definition is the indistinguishability-based definition. The second kind of definitions are simulation-based definitions. And indistinguishability-based notion is kind of de facto or the standard notion of security. However, we are going to use simulation-based definition, and the reason for that is there are two reasons mainly. The first reason is that it considerably simplifies our proof. Like once you work with those, our proofs are considerably more simpler. And the second reason is that if you could also define this partial security notion S epsilon in security, it actually just implies trivially an S epsilon sim security notion. So basically, they are roughly equivalent in some sense. So I'm just going to use the same notion. So let me now define what this notion means. So now, as I was saying, S is the size of the adversary in the game. So let's say you have an adversary A, which is a two-part adversary, A1 and A2, and both have size bounded by parameter S. Now, since we are talking about simulation-based notion, there are two distributions, real and ideal, and the security definition is just going to be some indistinguishability, some kind of indistinguishability between these two distributions. So, so I'm going to define these distributions now. The first step is common to both the distributions, real and ideal. And here the adversary A1 takes in the security parameter and outputs a message, a circuit C, and a state that adversary A might compute. Then in the real distribution, you run the setup of FE honestly to generate a key pair. Then using the public key, you're going to encrypt the message M honestly and compute the ciphertext. Then using the master secret key, you compute the secret key for the function C honestly. And then you give to the adversary's tuple R, which consists of the public key, the ciphertext, the secret key for the circuit C, and the state that A1 computed. In the simulation world, however, we don't do any of it. We just run the simulator algorithm of the FE scheme, which exists by definition. The simulator takes as input just the circuit and C of M, like the function value. And it computes bunch of fake public keys, fake ciphertext, and fake secret key for circuit C, and then gives to the adversary this tuple I, which consists of these fake keys and ciphertext and the state. And now, when we say that the scheme is S epsilon indistinguishable, we really mean that the probability that the adversary A2 takes in a tuple R, which is sampled from the real distribution, and it outputs 1, minus the probability that adversary A2 takes in the tuple I generated this way from the ideal distribution, and it outputs 1, this difference is bounded by epsilon. So that's really the S epsilon security notion. And in other words, I will just denote for being brief, I will just say that real ideal are S epsilon indistinguishable. So I'll come back to this notation very often. By S epsilon indistinguishability, I mean that the two distributions satisfy an equation like this, meaning that for all adversaries A of size S, these two distributions have an advantage bounded by epsilon.
Ayush,
Yep.
I have a question. This size of the adversary, is it going to come up later? So in the final definition that you want to achieve, you want to support any poly-sized adversary?
Yeah.
So why are we parameterizing it, especially over
because
here?
okay, so when you look at the theorem, which I'll just describe in the next thing, you start with something like this. S comma 1 minus 1 by lambda secure FE. And what you end up getting is something like this.
Oh, I see. So you
So
do change the size.
yeah, and remember, you at the end you need a sub-exponentially secure FE. So we start with something sub-exponential. So we get sub-exponentially small here. I'll come to this. Just give me a minute. I think I will be able to answer your question once I describe the theorem statement.
Sure, thanks.
Okay. So once we have this, let me now just jump straight to the theorem that we prove. We show that there exists a constant C such that if you assume that you have an FE scheme, which is this secure, S minus 1 minus S comma 1 minus 1 by the security parameter secure, and further you are willing to assume learning with error, which is secure against circuits of sub-exponential size, like 2 to the lambda to the C, then there exists a FE scheme which is secure for circuits of size S to the C, and the distinguishing advantage is 1 by S to the C plus 2 to the minus lambda to the C. Now let me spend some time just describing the significance.
Can I just ask you to just so that we can absorb these parameters? So what's happening? The size, if it's secure against this size S in simulation sense, then it will be secure against smaller size.
Slightly smaller.
Slightly smaller,
yeah.
But the advantage will be lower than before.
Exactly. So yeah.
So you're winning in terms of advantage, but you're losing a slightly bit in terms of size.
Yeah.
Okay.
Yeah, that's exactly what's going on. So let me now phrase it in some way. So suppose you had a so by the way, first let me stress about size. So suppose you start with a scheme which was secure for all polynomial size circuits. You get a scheme which is secure for all polynomial size circuits, right? Because S and S to the C cover all polynomials because they are just the degree is just constant away. Okay. Now, if you started with a scheme which was secure against sub-exponential sized adversaries, so if S was some sub-exponential, then this scheme will also be sub-exponentially secure, like secure against sub-exponential sized circuits. Okay. Now look at the advantage. So we are starting with basically 1 minus 1 by lambda, which is almost being close to a broken scheme, like which is 1 minus 1 by lambda is an advantage which tends which can be as bad as 1 as lambda tends to infinity. And what we are able to get is something like 1 by S to the C plus 2 to the minus lambda to the C. Now this part is negligible, but the other part, if you started with a sub-exponential, S being sub-exponentially large, you get an advantage which looks like this, where C prime is greater than 0. If you started with security for all polynomial size circuits, you'll get standard negligible security, meaning that this thing will be less than all polynomials, inverse polynomials. That makes sense? Okay. So this theorem is useful because now in order to construct IO, all you need to do is come up with a scheme which satisfies an advantage which is like not close to negligible, but it could be arbitrary constant, at least. In the least, it could be a constant less than 1. So, and this was useful also because in all these works that recently came up, including the work of Agarwal, Lin and Matt, and then ours, and then a few follow-ups, all of them, if you're willing to believe their assumptions, could only give you a security of less than 1 by poly for some polynomial. And then our theorem can be directly applied to give us a fully secure IO scheme. Okay, so now let us try to build some intuition of how a partially secure candidate can look like. So let's focus on S comma 0.1. I'm using 0.1 just because it's a nice number and I don't want to deal with like security functions of security parameters and so on and so forth. So let's just fix 0.1 as an advantage for the rest of the talk. So here is, I'm going to give you an example of how you can construct how one of the S comma 1.1 secure FE scheme looks like. So in order to build that, we are going to use a fully secure FE scheme. Okay, and then this candidate that we are building, FE2, this is going to be really simple. What it does, it set up a public key master secret key pair from the secure scheme. And now when you're encrypting, it generates a secure ciphertext using the FE1 scheme, using the secure candidate. And then it outputs this, the ciphertext with probability 0.9. With 0.1 probability, it just outputs the message in the clear. So this is just an example of, I mean, if you look at it, with probability 0.1, you're leaking the message in the clear. And with probability 0.9, you are revealing a secure ciphertext. So this candidate cannot be more secure than like advantage 0.1 because it leaks the message in the clear with probability 0.1. So, and in fact, you can write down a proof that you can show that it is in fact S, 0.1 plus negligible secure. So why did I tell you about this candidate? The reason is that now we're going to discuss the transformation. So I at least want you to see that the transformation makes sense for this particular weakly secure candidate, and like you should be able to see why kind of the security comes from that transformation. Okay, so so now let me come straight to the construction. So, okay, so here is the construction. You have an ingredient, which is S, 0.1 secure functional encryption, which gifted by God. And then what we want to do is we want to construct a fully secure functional encryption from this. So what we are going to do is that we're going to do some kind of parallel repetition. And for those of you who know, parallel repetition have proven useful in various security amplifications. And there is a long list of things that you can parallel repeat and amplify security of. And in this particular construction, let's just say that the repetition parameter that we're going to use is security parameter. Okay, so here is the here's what you're going to do. Suppose you have a message M, right, and you want to encrypt this message M and construct a secure scheme, which encrypts M securely. So what we do, we're going to secret share it using some special purpose secret sharing scheme. And I'll just define this special purpose secret sharing scheme in just a minute, but it is known in literature by the name of homomorphic secret sharing. So you secret share it using this scheme and compute T shares. And then if you want to encrypt this message M, in the setup, you will have T independently generated master secret key and public key pair. So this I will run using FE setup T times. T times. And then under public key PKI, you can encrypt the share SHI. So this is roughly how the ciphertext looks. Okay. And I'm going to describe this in formal detail, like the scheme, but roughly this is the intuition. And now the intuition is that since the secret sharing scheme, even if you leak T-1 shares, you have some security. Hopefully some of the FE encryption should hide some of the shares to argue, so for us to be able to argue security. So that's like just a very, very high level intuition. Okay, so now let me define this notion of homomorphic secret sharing in order to be able to see the scheme in more detail. So what this homomorphic secret sharing does, it takes in a message M, and then you can secret share it into shares SH1 through SHT, as I was mentioning. And then what's so nice about this homomorphic secret sharing is that you can evaluate on these shares locally using any circuit C, using this eval algorithm that homomorphic secret sharing is equipped with. Okay, so you generate these evaluation shares P1 through PT, and they in order to compute a share PI, all you need to do is let's locally compute in that particular share SHI. Okay, so and also this algorithm is actually deterministic, and it's polynomial time, of course. Then what you can do is that once you have all these evaluation shares P1 to PT, you can run a decode algorithm, which is also part of HSS, and it's a relatively simple procedure. And then you can recover C of M. So that's the functionality. Now there are also some properties efficiency. which is only going to be used in our scheme to argue compactness. But nevertheless, let me tell you what it does. What is it about? So the size of each share that you compute, that's small. That's the first efficiency property. That the size of each share is small. How small? It's like length of the message times some polynomial and security parameter and the depth of the circuit C. Okay, and then the size of evaluation circuit, that's also small. In fact, it just grows linearly in the size of the circuit times multiplicative overhead of polynomial in lambda and d. Okay, so that was efficiency. Now comes the main point. What's the security? So security says, let's say you have any adversary A, which is polynomial time, of course. What it does, it's able to corrupt some t-1 shares. So let's say this is some set S, where the size of the set is t-1. Let's say it gets access to t-1 shares of his choice. And then he can also ask for eval query on the remaining share. He can ask a query like that. Then whatever view that this adversary gets, which consists of t-1 shares and the remaining share, that should be simulatable using the HSS simulation algorithm. So he took a set S, and then he gets to learn this, right? And this is simulatable using HSS simulation algorithm, where the simulation algorithm only takes as input the circuit C of M and the set of corruptions. It doesn't take the message as input at all. So that's the security notion. And the good part is that it can be built using LWE. In fact, you can use any of LWE-based FHE scheme off the shelf and then use it to construct this notion. So this is known in, I think, quite a few number of words. So I won't be talking about how you can construct that. So now,
Aayush?
Yeah.
Question. You don't need this property that the HSS output can be computed as an XOR of the local.
No, I don't need that at all.
Okay, good. Okay, good. Thanks.
Okay, so okay, so now let me describe the scheme in more clarity once we have the notation at hand. So the setup, as I was telling, consists of just the independent instantiations of FE setup, and the public key just consists of concatenation of all public keys, PKIs, and master secret keys concatenation of all MSKIs. Encryption algorithm takes in a message M, secret shares it into shares, and then outputs this, like PKI encrypts SHI using the FE algorithm and outputs just these street ciphertext. Key generation is going to let you compute. You run FE keygen using the key MSKI for this homomorphic evaluation circuit that you just saw, and you're going to publish these T keys. And you can see that once you have these keys and these ciphertext, you can recover these evaluations P1 through PT, and then the decryptor can decode and learns C of M. So functionality-wise, this makes sense. Okay, so now let us do some sanity checks on this particular transformation. Let's just look at the canonical candidate that I told you, the S, 0.1 secure one that was revealing the message in the clear with 0.1 probability and was giving out a secure ciphertext with probability 0.9. So, so there, if you instantiate that particular candidate in this transformation, and we are making T repetitions, then you are on an average going to leak out about 0.1 T times shares in expectation. Why is that? Because that scheme leaks out the message that you encrypt with probability 0.1. And so therefore, in expectation, you're going to leak out those many. In fact, if you look at probability that every share is going to leak out, that is going to be bounded by this number 0.1 to the T. Basically, they are all independent events. So it's going to be 0.1 to the T. And this is actually very small. This is negligible. And under all other circumstances, when less than P-1 shares are leaked out, then you know that you can rely on, like under all those other circumstances, you can use HSS security to argue that I feel like to argue, I mean, security. And in fact, you can formalize this argument and write down a proof. So, but this was about like a very particular candidate that I told you about, like the one which has a very nice structure. How do you prove security in general? And that's really the question that I want to answer in the next few minutes, like next part of my talk.
So Ayush, one more question, if I may. So one way to do this sort of like secret sharing and computation is just sort of secret share using polynomials like Reed-Solomon secret share, right? And then if you compute, if the degree of your computation is small enough and you release enough shares, then you can do this you can do this, right? You can do like an FSS like local computation and then reconstruct the answer.
Yeah, so FSS, like I agree with you. So you are talking about the GBW construction,
That's right?
Kind of.
That's right.
Yeah. So so actually, yeah, that it might be, you might be able to do that, and I think so. We also have a follow up where we do something else, like other than using homomorphic secret sharing. This is this particular thing is just for only for like intuition, and it's, I think, more simpler to describe.
Okay. Yeah.
So you might be able to do that.
Okay. Sounds good. Thanks.
Okay. So how do you prove security? Yeah. So okay. So for some time now, I'm going to for a few minutes, I'm going to talk about something abstract and vague, which may or may not make sense. But I promise you that, like as soon as I'm done, I'm going to give you something formal to look at. So here is actually, if you look at the problem from like on a high level, here is the problem. You have a so let's say this is a set of randomness, and then there is some procedure which where you have this R which is inside the randomness, and there's a procedure I that allows you to generate some hard problem for an adversary, and you are given a promise that probability over R, IR is hard for all for an adversary A of size S. You're given that this is 0.9. And what you want to do is to come up with an analogous setting where this holds that probability. So now you have R prime, and R prime is the randomness. Probability over R prime, I prime, R prime is hard, right? So that's what your goal is. But how do you make this jump? You're talking about some advantage which is not close to 1, and you want to go close to 1. So now it turns out that in many of these circumstances, in many of these situations for various notions of I, what you can do, there will often exist something called hardcore set or a hardcore set theorem, which roughly means that in many of these circumstances, what happens is that you can show that if this promise is met, then there will exist a set S such that the size of the set is big. So it's going to be 0.9 times roughly like that. But what this lets you do is that when you sample this randomness from this set now, then IR suddenly becomes hard for any fixed adversary of size less than some S double prime related to S. This becomes close to 1 minus negligible. And this notion that lets you do this is actually a hardcore set. What it says is that in many of these circumstances, when you have this promise, you'll have a good set of randomness where if you sample randomness from there, the problem is actually very hard for any adversary of slightly smaller size. And this, in many applications, lets you to do this switch. So let me just now talk straight about this hardcore set theorem that we are going to use. This is an indistinguishability hardcore set theorem, which was due to Maurer and Tesaro in TCC 2010. which roughly says the following. It says that take any function CNF, arbitrary functions, which output n bits to m bits. And if I give you a promise that Ex, when X is sampled at random, and f of y, when y is sampled from random, they are S delta indistinguishable for some Sn delta. Okay. So the premise is that Ex and f of y, they are indistinguishable, S delta indistinguishable. Then for any desired level of security you want, any desired level of security, any desired advantage that you want, there will exist two sets SE and SF, which are big enough. They are how big? They are 1 minus delta times 2 to the n. Delta was the advantage, maximum advantage in the initial indistinguishability. So these are big sets, but now if you sample Ex from this set SE and Fy where y is sampled from SF, these two becomes epsilon indistinguishable for all adversaries of size S prime, which is an S prime is like almost as large as S, only slightly smaller. And how smaller? It will be, you'll have to pay a factor of epsilon square in multiplicative terms. If you want more security, you will end up getting security for smaller size circuits. If you want, yeah, so that's about the hardcore set theorem. Is the theorem clear or should I repeat it again? Okay.
So Aayush, I have a question.
Yeah.
Sorry.
Go ahead.
Oh, I want to ask. So this theorem is saying that there exists, this set SE and SF. It doesn't talk about finding the set, right? So
yeah,
I just want
it
to
exists.
make sure
Existential.
it's existential.
And in fact,
so you
I want to
just
point
need
out
it in like some kind of probabilistic argument later.
Exactly. So I want to also point out that SE and SF, they may not be efficient to compute, and they might actually depend on descriptions of E and F, for example. Okay. So now let's just, once we have this theorem, let's just try to get our hands dirty and try to write down the code. Okay. So here is the first hybrid, which consists of the real world that the adversary sees. The adversary sees PK1 through PKT, the public keys that were sampled T times and independently. Then he sees T ciphertext, where each ciphertext CTI was FE encryption of the share of the message using the public key PKI. And similarly, you have T function keys, which were keys for the eval function of the homomorphic secret sharing. So this is what the adversary sees in the real world. Now we have seen this theorem. Let me try to write it in the same notation kind of. We are going to define two functions E and F. In fact, we are going to, for every index in T, we are going to define T functions. So EI be the function which takes Xi as in the input as the randomness, and then it's going to compute the distribution for that index. So for E1 will produce this. So EI is going to produce PKI, SKI, and CTI using Xi as randomness. And note that in order to do so, the share SHI is going to be hardwired in EI. So I'm just, this is like a slight detail. And then I'm going to define FIXI is the...
Sorry, Aayush, can you remind us what is XI here?
XI is an input to this function. I'm defining a function now. So we had these functions, right? E and F.
But how does it relate to the original construction?
Yeah. So EI takes Xi as input. And basically it's the randomness for generating the ciphertext for that input. So EI takes Xi as input and uses Xi as the randomness to generate the ith tuple, like the ith tuple which consists of public key, secret key, and the ciphertext.
Yeah,
and in order to do so,
just making sure it has nothing to do with the message of FE.
No, message is always M for the talk.
Okay.
Okay, and similarly, Fi is the other function. What it does, it just, for the ith index, it's going to simulate the public key, ciphertext, and the secret key using the FE simulation algorithm. So the simulator takes as input the eval, and it takes a value which is the evaluation of that share, like applied on the circuit C, and it takes randomness xi and then runs the simulation algorithm to recover this. Okay, so that's the Fi. Now observe that due to Fe security, Ei and Fi are actually S, 0.1 indistinguishable, right? That's the security of Fe. That means there must exist two hardcore sets SEI, SFI of big enough size, satisfying the premise of the claim of the theorem. So you have two hardcore sets which are big enough. And I also want to point out that EI actually depends on the share. Fi, however, does not depend on the share I, but it depends on eval applied on that share. Okay, so now let's down the hybrid in this notation. So hybrid 1 is just rewriting the hybrid 0 like this. So the hybrid is just E1 x1 to ET xt, where x1 through xt are chosen at random. So far, so good. Now, so far, we have not been able to use the theorem because we just reiterate in the main hybrid. So in order to move to a setting where we can use the hardcore sets, let's consider this two distributions. Let's just say that we are sampling x1 from uniform. Sampling this is identical to doing what I will be doing on the right with probability 0.9. Sorry, with with probability 0.9 sample x1 from the hardcore set SE1, and with probability 0.1 sample x1 from the complement. Okay, now these two things are identical. Why? Because sampling from uniform is the same as sampling from a fixed set with probability the density of the set, in which case it's 0.9 in this particular case, and with remaining probability you sample from the complement. Okay, so these two things are exactly identical. And now rewrite the hybrid in this form. For every index, we have these hardcore sets of density which is large enough. So here's what we're going to do. We are going to sample an alpha, which is in 0, 1 to the t, where each alpha is 1 with probability 0.9 and 0 otherwise. So this alpha is just bear with me for a moment. It's just going to indicate whether you are sampling from the hardcore set or from the complement. Okay. So now suppose we have an alpha which is sampled this way. For example, this in the string, at least on an average 0.9 of them are going to be ones. So wherever we see a 1, we are going to sample from the hardcore set. Wherever we see a 0, we're going to sample from the complement. And then the hybrid is just computing E1 on x1, E2 on x2, E3 on x3 on whatever randomness we chose in this step. And now hybrid 1 is identical to hybrid 2.
Aayush, there is a question here. Can one efficiently sample from SE and SF?
No, you can't sample efficiently from SE and FM. I mean, there's no guarantee in doing that. Does that answer your question?
Yeah, well, yeah.
Okay.
Yeah.
So so hybrid 1 is identical to hybrid 2, but now we have made a slight bit of progress because we have been able to manage from hardcore sets. So now we can use the lemma in order to make progress. So in this hybrid, it's just the intuitive step. Wherever we see a EI xi, where xi is sampled from SEI, we're going to switch it to Fi of xi, where x is now chosen from the other hardcore set. So for example, we had this in the previous hybrid, right? So now we are going to switch it to F wherever there's a 1 because of the hardcore set theorem. But wherever we do not have a 1, wherever we have a 0, we can't do anything about it because we are talking about sampling here. The randomness was sampled from the complement, and there's no security guarantee associated with when the randomness is sampled from the complement of the hardcore set. So you can't switch that. So we get something like this. And again, in order to argue this, actually, I'm hiding some details under the rug. This is just because all these functions in the hardcore sets, they might be inefficient to sample with. So in order to make these reductions, you have to be a little bit careful and do some kind of non-uniform fixing arguments. And therefore, I'm not going to talk about it, but I can answer it offline if someone has any questions about it. Okay, so the hybrid has this structure. Now the question is, are we done yet? Because you remember each alpha is one with very large probability, it's 0.9. So some of the EIs are now switched to Fi in this hybrid. And Fi, if you remember, only depends on the eval, right? Fi actually just depends on the evaluation of the shares, something like this. So now the question is, it's no longer directly depends on the share. Can we use homomorphic secret sharing property at this point and argue things makes security go through? The answer to that is no. The reason is because we are sampling from these crazy sets and they are very inefficient. They may, in fact, there are two problems. The first problem is that it's inefficient to sample from such sets. At the same time, actually, both SEI and SFI can depend on share SHI. So really, like, everything depends on everything. So how do you make security reduction go through?
So don't want to interrupt much, but you're kind of 2 minutes over time, but you are running on the time that Amit donated you.
Yeah. Thanks for telling me. I'll just take three more minutes. Okay. So so the main idea in order to fix this is that we observed that the density of each set's SEI and the complement is actually pretty big. They are constant dense sets. And so if you look at this alpha string that we sampled, for every index, it has just a constant amount of information. So actually, a random sample from this set is not going to have too much information about the shares. And we just need to somehow capture this and write down a proof. So the main contribution of our work is that we build an efficient circuit H using some techniques, which takes an instance of the form alpha, the shares, and the evaluation shares, as in the previous hybrid that I just showed you. It takes that, and it somehow outputs randomness x1 tilde to x2 tilde, such that now this x1 tilde to x2 tilde looks like the actual randomness that you were sampling in the previous hybrid, but now this circuit H is pretty small. I mean, it's not small, but it's reasonably small so that you can make the security proof go through. So that's our main contribution. And in order to do that, we actually rely on we actually introduce some really cool techniques. And unfortunately, I don't have time to go over that. But what it lets you do is that it really takes you to an efficient hybrid where you just output something like this, where these entries are sampled from H, and now it's just efficient and you can make the proof go through. So this is our simulator, which is a really succinct looking simulator. Apply some bounded function on homomorphic secret sharing simulator output. So with that, I would like to conclude, and I'll be very happy to take some questions offline if there are any.